Section 2.5, Understanding Amazon Aurora's I/O Architecture. In this section, I'll dive deeper into Amazon Aurora's input-output, or I/O, architecture. Amazon Aurora, as you'll learn more in a subsequent video in this 2.0 series, has tremendous performance. Databases are all about I/O, so the fewer I/Os needed, the better the performance. Network-attached storage is all about packets per second. After a certain point on Amazon EC2 with network-attached storage, it won't scale past a certain point, so you have to minimize the amount of network packets that cross the network. High-throughput processing doesn't allow context switches. Context switches are computationally intensive. Context switching involves the process of storing and restoring the state or the execution context of a process or thread so that execution can be resumed from the same point at a later time. So a lot of the performance improvements made in redesigning the relational database to be what is known as Amazon Aurora today had to do with doing fewer I/Os, reducing the number of packets per second that they're driving to storage, and moving to more asynchronous processing. Let's take a look at the differences in I/O traffic between Amazon RDS MySQL and Amazon Aurora. Here you see a representation of what a MySQL database running on Amazon RDS would look like with standby. You have your primary instance in one availability zone, and you have your standby instance in another availability zone. When you do a write to the primary instance, it will write the data against the attached elastic block store, or EBS. Then the EBS service will automatically mirror that data to another EBS volume to have the durability and availability that EBS gives you. And that same write operation is issued to the standby instance. And again, that standby database will write to the EBS volume that's attached to it, and that EBS volume will write to the mirror. But it's not just the data write, seen by the red arrows, that has to be done. There's also a lot of log files that need to be moved around to the different layers, and the standby database and its layers, seen by the green arrows. Looking at the images, there's a lot of moving around of different parts of that data and the I/O operations that have to happen in order to have a complete success message and to have everything in sync between your primary and your standby database. Then, when you start to think about network jitter, which is the variation in packet delay at the receiver of the information, or latency that might play into this equation, you have a situation where those things can impact your primary instance and its standby instance, where you might not feel comfortable about the state of things or if you can recover successfully. On the slide, you'll also see that a performance test was done, but I'm going to address performance benchmarkings in a subsequent video in this 2.0 video series. However, take note of the results. They got 780,000 write transactions in 30 minutes and about 7.4 thousand read-write I/O transactions per million transactions. This was only tested on the primary instance because the standby database is part of the Amazon RDS service, and what's really relevant is what's happening on the primary database instance. Let's now look at I/O traffic on an Amazon Aurora database. Notice the word database is purple because in the next slide, we'll be looking at I/O traffic in Amazon Aurora storage nodes. The Aurora team worked to reduce the amount of I/O that happens on the Aurora database by changing the architecture. One difference is that the only thing the primary instance is doing to the storage layer that spans the multi-availability zones is sending redo log files to that storage node. It collects them up, which is also known as boxcaring, combining them together and sending them in regular chunks to the storage node. The redo log files are small, and batching them up beforehand really helps reduce network I/O being sent across the wire. Once the log files get to the storage layer, They do 6 times more writes than you'd see in MySQL because they're writing it all to all 6 nodes. But it ends up being 9 times less network traffic compared to what you'd see in the MySQL configuration and all the writes that have to be done to its storage system. This allows the Aurora cluster to be a lot more tolerant of what's going on from a network standpoint because it's sending small amounts of data to start with, thus any little hiccups that might occur are less impactful to what's happening from the Aurora cluster standpoint. They ran the same benchmarking test on Amazon Aurora that they did on MySQL in the previous slide. The result is that they were able to write 28 million transactions, which is 35% more than what was achieved with MySQL. That works out to about 950,000 I/O operations per 1 million transactions. This has 6 times the amplification because of the 6 storage nodes. If you broke that down, it's about 150,000 read-write operations per storage node. That's about 7.7 times less than what it took from a MySQL standpoint. The way Aurora is made, it's able to do more because in the background, it's doing a lot less as far as I/O is concerned. Let's now look at I/O traffic on an Amazon Aurora storage node. And again, notice the word storage node is in purple. The primary instance is going to send log records to the storage node. The storage node is going to put that into an in-memory queue. Notice the words incoming queue of different colored squares by the green encircled number 1. Then it's going to pull off that queue and persist that data and write it to disk. At that point, the data is durable on the storage node and it would acknowledge back. Notice the acronym ACK near the green encircled number 2 to the primary instance. And at that point, all interactions with that primary instance is done. That is the critical path from an Aurora standpoint. Everything else is done asynchronously and can happen independent of communication with the primary instance. Once the storage node has its log files, it's going to start organizing those log files and the records in those log files because things can chill up out of sequence or not show up at all sometimes. It'll find out, do I have everything? Am I missing any writes? Is anything out of sequence? This step is shown by the green encircled number 3. Remember the water cooler image from video chapter 1.0 when discussing peer-to-peer gossip? Well, at this point, by the green encircled number 4 is where all 6 storage nodes begin the peer-to-peer gossip network that helps all 6 nodes talk to each other and resolve conflicts where maybe one of the nodes is missing data. The nodes sort all that out and exchange data so that all the nodes have the same amount of data and that all missing data or conflicting data is resolved. Once that's done, they coalesce the log records into new data block versions, seen by the encircled number 5. Then periodically and asynchronously, and very frequently, those storage nodes will back up the log and the block data to Amazon S3, seen by the encircled number 6, implying this is our new storage used for our database. Storage nodes will also go through garbage collection, seen by the green encircled number 7, looking for old log files and data blocks that have been replaced and get rid of those. Finally, it will do data scrubbing, seen near the green encircled number 8. It rereads data blocks independent of requests from the database instance and verify checksums against those blocks to ensure they're still good data blocks that haven't been corrupted through normal disk usage or that they're dirty now. If they do find a bad data block, they leverage the peer-to-peer network again, and they'll heal themselves across that network so everything is fine again. Some things to note. The input queue is 46 times less than in MySQL I/O, unamplified per node. They get the foreground latency path done in the first 2 steps out of the way, making everything else asynchronous. The storage tier is multi-tenant, so there's going to be patterns in high usage and low usage during the day on that storage tier. So the team worked to take advantage of the low points to get a lot of these asynchronous jobs done so there's no negative impact on the customers, but still get all of the work done in a decent amount of time. Another architectural change done in Amazon Aurora is the way commits happen. Traditionally, the way that commits work is somebody does a write, and those writes are collected in a buffer. When either the buffer is full or a certain predetermined time has passed, the buffer will get flushed and written to disk. The problem with this is whoever was the first writer will get a latency penalty. If not enough reads happen, they have to wait for the timeout flush to happen. On the Aurora side, this doesn't have to happen. And it doesn't. This is because Amazon Aurora was built with its own code base and are interacting with their own code that the Aurora team wrote. They don't have to live with the Linux file system on how to do commits. So how this works is as soon as the first write happens, they start I/O operations. Every write gets its own I/O. It's not waiting for anything else. These writes are collected in a buffer, and a background job collects them at some point, and they're sent off to the storage node. They're considered durable when 4 out of the 6 storage nodes acknowledge, yes, I've got the data and I've committed it to disk. Then they look at the last log record number or log sequence number or LSN. In this case, it's number 47, and the system asks, who below this number needs an acknowledgement? And they're going to acknowledge back to all the numbers below that the write was successful, and at that point, they consider the database durable up to this last record number, and then it advances from that point. Another architectural change done in Amazon Aurora is they re-engineered the thread pooling. Today, with MySQL, every connection gets a thread. And as more connections happen and the database is more heavily used, this can be a problem, leading to performance challenges. Some of this is solved with MySQL Enterprise Edition, where thread groups are used. If it sees a long-running connection, it'll add another thread to accommodate that. But it's kind of a workaround where it requires careful stall threshold tuning to add threads in the right places so there's not too many threads, which will burden the database, or not add enough threads, which will delay getting things processed. So on Amazon Aurora, from a thread point, everything connects via an ePoll function. Behind ePoll is a latch-free task queue that has a bunch of threads that aren't doing any work and are available to do work. Because these are independent, threads are able to scale up or down threads dynamically depending on the amount of pending transactions or connections coming into ePoll. What's really cool about this is it's aware of when a transaction is awaiting a commit. While awaiting that commit, the thread can be repurposed and let it go and do other work and have other threads to hang around to wait for the acknowledgement of the commits when they happen. This helps threading get the most out of what it's already allocated. This means Amazon Aurora can gracefully handle 5,000 plus concurrent client sessions on the largest Amazon Aurora instance, R3-8XL. Quiz time for section 2.5, Understanding Amazon Aurora's I/O. Question: what isn't a way that Amazon Aurora has improved I/O? A. I/O traffic is improved by sending smaller packets from the primary instance to the replicas. B. Amazon Aurora storage nodes work synchronously from the peer-to-peer gossip stage to get the heavy work done up front. C. I/O is improved through the way database commits occur. D. I/O is improved through connection threading via ePOL. Answer: B. Amazon Aurora storage nodes work synchronously from the peer-to-peer gossip stage to get the heavy work done up front. Explanation: for each node, the synchronous work is done once the update queue acknowledges back to the primary instance that things are done. The remaining steps are asynchronous, including the peer-to-peer gossiping. This concludes section 2.5, Understanding Amazon Aurora's I/O. Coming up next is section 2.6, Understanding Amazon Aurora's Scalability and Elasticity Architectures.